So exercise related to Doppler effect and the pulse echo. We discussed this question last session, so we'll move on. And question 4 also done. Question 5, the diagram shows a line spectrum which is produced by a particular element which is viewed in the lab. Then as a star containing the element is moving away. So whenever object move away, what will happen? The wavelength will increase. The observed wavelength will be higher. Or we'll observe the wavelength increases or shifted towards the longer side, or we call the red shift. So the whole spectrum will shift towards the red. So when we check the spectrum, the pattern of the spectrum will not change. Pattern of the spectrum means, like example, you can see the first line, then the second and the third line, fourth, fifth, and sixth. So pattern should not change. The only thing what should happen, the whole pattern should shift towards, if the object is moving away, it will shift towards the red, which called red shift. If object is moving away, the wavelength should increase and red shift. If object is moving towards, it means we'll have a blue shift and the wavelength should decrease. So whole pattern will shift. When we check the option, why A is wrong? According to A, the pattern has changed, like it is completely inverted. The what was there on the right become left, and what was there on the left become right. That's why A is wrong. Why B is wrong? The same thing, what happened in B, the pattern expanded right and left both sides, but practically it's not possible. Like if either the object is moving towards or away, it cannot move both directions. So that's why it cannot be B. When we check C, the pattern is same for C, but it is shifted towards the blue or the violet, we can say. So it means if it is shifted towards the blue or the violet, it means the object is moving towards. And the whole pattern is shifted towards the left hand side, towards the red hand, towards the red. So it means the object is moving away. So in a Doppler effect, when the source is there, and on earth we are observing, like we are observing any star or the galaxy. So if this source or a star is moving away from us, so what will happen? The wavelength which we receive, the wavelength will be longer wavelength, or wavelength will increase. So the whole pattern will shift towards the longer side, or red side. That's why D should be the right answer. Is it clear? This question, the concept of the red shift. So whenever object move away, we'll have a red shift, and object move towards, we'll have a blue shift. So the whole pattern, the pattern should not change. One thing, the whole pattern will shift either towards the red, or it will shift towards the violet, depending on whether the object is moving towards or away. In question 6, the velocity of a longitudinal wave in a spring is also determined by finding the time for a pulse to travel along the length of a spring. The spring is filled while the pulse is created at the bottom, allowed to reflect, and the pulse travel up and down the spring. So how many times? Show that the velocity of a longitudinal wave in a spring determined by this method is about 5 meter per second. The time taken is 6.17, and the length of the spring is 72 centimeter. So if it is the length of the spring, so there's a spring which is having a length of 72 centimeter, or we can say 0.72 meter. the time taken, like the pulse is sent, the pulse travel and bounce back. So the time it took to travel and return back, that is 6.17, but that is the number of the times. So it's about 42 times are there, or 21 times actually. So this is 21 times. So 21 times the pulse sent and bounce back. Like it is vibrate, going, coming back, going, coming back. It's about 21 times. The pulse travel up and back down the spring, and shows the velocity of a longitudinal wave in a spring determined by this method is about 5 into 5 meter per second. So this is a time the pulse is taking for 21 times. Like this is a total time. So first we'll find the time to travel towards like end from end one, A to B, and then return back. And this spring is not horizontally placed; it is placed vertically. So first we'll find the time for one vibration, we can say, or a time period. So that time is equals to the total time, which was 6.17 divided by 21, because 6.17 is for 21 times, but we need for one. So this is 6.17 divided by 21 equals to 0.29. So 0.29 second is the time it take to travel back and forth. Now, because it's a reflection, whenever there's a reflection, the formula speed is 2d divided by t. So speed is equals to 2 multiplied by distance. How much distance? That is 0.72, and time is how much? 0.29. So 0.72 multiplied by 2, 1.44, and that is divided by 0.29. So this is 1.44 divided by 0.29. So the total time, the speed at which the wave is traveling is about 4.96 meter per second, which is approximately 5. So we know the time for the 20 oscillation. We first get the time to for one, and then because it's a reflection, so speed is 2d divided by t. If wave there is no reflection, then we'll use speed as distance over time. In the question, there's a reflection, so it will be 2d divided by t. Is it clear discussion that how we work out the speed of this wave in a spring as it traveled 21 times back and forth? Then question number 6, the ultrasound is used to investigate the blood in arteries in a human body by detecting the Doppler shift. So the movement of the blood can be investigated in the artery by using a Doppler shift, because what happened, as the blood is flowing through the arteries, the ultrasound sent and it will bounce back. As a result, when these ultrasound will bounce back, we can find, because the Doppler effect can be used to find the speed at which the object is moving. So as the blood is flowing through the arteries, it will give different shift. It will give a, if it is moving towards the source, it will give blue shift, and it is moving away from the source, it will give red shift. And first we can find a Doppler shift. The Doppler shift is equal to change in wavelength divided by original wavelength. or Doppler shift can be used to find change in frequency divided by original frequency. So after getting a Doppler shift, the Doppler shift is equal to speed of the object divided by speed of the wave. Normally we use, like, because ultrasound have different speed in different medium, so this is always the speed of the object and this is the speed of the wave which we use. If we use light wave or radio wave or microwave, it will be 3 exponent 8, but ultrasound will have different speed in different medium. So the question is, the Doppler shift is used to measure what? What is the purpose of the Doppler shift? Using a Doppler shift, we can first identify whether the object is moving towards or away. That is one thing. The second thing, we can identify the speed of an object, like at what speed actually the object is moving. So it is used to find the diameter of the arteries. That's wrong. The size of the particle in the blood, it does not identify size of the blood particle. Temperature of the blood particle is not used to find the temperature. Basically it can be used to find the velocity at which the blood is flowing through the arteries. So the Doppler effect can be used to identify whether object moving towards or away from the source, or whether source is moving towards or away from the object. And the second thing, it can be used to find the speed at which the object is moving. So here the object is a blood. The blood flow through the arteries, cause a Doppler shift, and using a Doppler shift we can work out speed at which the blood is moving. Is it clear? Question 7. Any doubt till this point? Then question 8. When a light from a distant star reaches the earth, the wavelength appear to shift it to the red end. So it means it become longer. What we can say about the star, we can say that this star is moving away from us, because if it is the wavelength decreases, it means it is moving towards, and if the wavelength increase, it is moving away. So if there is a star far away from us, and on earth we receive the radiation, and we compare the wavelength received from the star with the same element in the lab, and we found that this is a longer wavelength. So if this is a longer wavelength, what we can say about the star? We can say the star is moving away from us, or it is giving a red shift. So this is because, what is the reason? The distance traveled by each successive wave has increased. That's true, because the wavelength has changed, or it become a longer wavelength. If the wavelength become longer, it means the distance traveled by each successive wave has increased. So that is giving an idea. What about the other option? When we check, the frequency of a light emitted has decreased. Remember, the light emitted is not changing. Only what happened, what we receive has changed. Star is emitting out the same wavelength. Like example, if this star is having hydrogen, and on earth we have hydrogen. So if I say, in the lab, when we carry out this infrared this line spectrum of hydrogen, it was giving out 400 nanometer. So star, which is also consists of this hydrogen, that is also giving 400 nanometer, the wavelength, or 700 nanometer, 400, any value. But as a result, because this star is moving away, then the wavelength which we receive will be different. Like we might have 450 nanometer. So that what is emitted out from the source never changes. It is what we receive has changed. So the frequency of a light emitted has decreased. That is wrong. The frequency does not decrease. If the wavelength increase, the frequency should decrease. But that is not from what is emitted out. It is emitting out the same frequency, but what we receive has changed. So it cannot be B. When we check option C, the speed of the star has increased. We cannot identify whether its speed is increasing or decreasing according to the information given. Then the star is emitting out a longer wavelength. That is also wrong. Star is emitting out the same wavelength, but it should have, like according to the element, but because it is moving, what we receive has changed. So whenever the source, like example, in terms of frequency also we can say the frequency of the radiation, say with the hydrogen is example 100 hertz, and the frequency of the radiation which is on the star is also the same 100 hertz. But when the star is moving away from us, the wavelength become longer and the frequency which we receive becomes shorter, maybe 80 hertz. But that is what we receive, not what is emitted out from the star. Star is emitting out the same frequency and wavelength that what we receive, what we have on Earth. But due to the relative motion of the star or the observer, the Earth, there will be a change in the wavelength or frequency. So the other option, B and C, why they are totally wrong? Because they mention light emitted. So light emitted does not change, only what we receive has changed. And the speed of the star has increased, that we cannot determine from the information, that speed, whether it is increasing or decreasing. It should have, like the wavelength is continuously increasing or decreasing, we can identify the speed, but not with this information. Is it clear, question 8, that how we work out that A is the right answer? The next, early experiments to measure the speed of light involve the timing of the pulse of a light being reflected from a distant mirror. And if a pulse of a light was emitted and then deflected in 0.24 millisecond, what is the distance between to the mirror? So like there's a mirror and we have a light source. So the light is sent, which hit the mirror and bounce back. So whenever there's a reflection, the formula speed is equals to 2d divided by t. The question is, what is the distance between the mirror and the source? So we need distance. So distance should be speed multiplied by time divided by 2. What about speed? Speed of all electromagnetic radiation. It's 3 into 10 power 8 in air or vacuum. The time it took 0.24 milliseconds. So it will be 0.24 into 10 power minus 3. And divided by 2. So when we simplify, it will come out 3.6 into 10. These are exponents actually. It's not like 104. It is 10 power 4. This is 10 power 4, 10 power 7 and 10 power 7. When I'm converting the Word document to PDF, so sometimes the exponents are changed. So this is actually a power. So 3.6 into 10 power 4 meter is the right answer for this. So when there is a reflection, the speed is 2d divided by t. If there is no reflection, then speed is distance divided by time, as a wave does not accelerate within the medium. Stationary observer hear the sound emitted by a moving source. This produces, like there's a moving source. So source is there which is moving, either move towards or away, and stationary observer is there. Observer is not moving or observer is stationary. This produces a Doppler effect. Doppler effect means there will be change in the frequency or the wavelength which the observer receives from the source. Source is emitting out same source, frequency and wavelength are not changing, but due to the motion of the source, the frequency and the wavelength will change. So there is a change in frequency of a sound emitted by the source. That is totally wrong. Source frequency and the source wavelength are not changing. So this option is completely wrong. Like emitted from the source can never change. Then here there is a change in velocity of a sound emitted by the source. Again, that is also wrong. Because what is emitted, the frequency, the wavelength, the speed of the wave which is emitted by the source is not changing. what we receive, what the observer receive will change. So due to relative motion, like if the source is moving towards the observer, what will happen? The wavelength which is received by the observer, that will decrease and the frequency will increase. And opposite will happen if the observer and the source, if the source is moving away, then the wavelength which is received by the observer will be longer and the frequency will be shorter. So there will be a change in frequency of a sound heard by the observer, that is true. And then there's a change in velocity. Velocity of the wave is not changing. Speed of the object or the source can change, but here in the observer is stationary, so speed of the source can change, but not the wave which is emitted out. The speed of the wave, even it's a sound wave or a light wave, does not change when it travels from source to observer. Is it clear, question 10, that there is a change in frequency of a sound heard by the observer? So Doppler effect state there is a change in frequency on the wavelength due to relative motion of source or observer. In question 11, ultrasound scanning can be used by doctors to obtain information about the internal structures of a human body without need of the surgery. The pulses of ultrasound are sent into the body from a transmitter placed on the skin. The ultrasound uses a frequency of 4.5 megahertz. State why wave of this frequency called ultrasound. So why we call this ultrasound? Because there is an audible range. What is the audible range? The audible range is from 20 hertz to 20,000 hertz. So any sound frequency which is more than 20,000, it is known as ultrasound. So because this is about 45 megahertz or 4.5 megahertz. Mega means 10 power 6, so it's more than 20,000 hertz. That's why we call this sound as ultrasound. So the answer here, because this sound is having a frequency more than 20,000, so it refers to ultrasound. Then a pulse of ultrasound enter the human body and its reflection return to the transmitter about 1.6 into 10 power minus 4 second. Like, so say this is a human body, the ultrasound sent and then it bounced back. How much time it took? 1.6 into 10 power minus 4. Calculate how far the reflecting surface is below the skin. So, and we assume here that this is the place, the source of the ultrasound, which is a transmitter and the receiver, both are there. The average speed of the ultrasound in human body is 1500 meter per second. So whenever there is a reflection, the speed is 2d divided by t, where speed of ultrasound is 1500, then the distance we want to find and time is 1.6 into 10 power minus 4. So speed is equals to 2d divided by t. The speed of the ultrasound is 1500. 2 multiplied by d divided by time is 1.6 into 10 power minus 4. This is divided, other side multiplied. So 1500 times 1.6 into 10 power minus 4 divided by 2. So when we divide this, the distance will get about 0.12. So 0.12 meter is a distance. This d is 0.12. Distance between the source and the reflecting surface. State why ultrasound are transmitted in pulses. What is the reason? Whenever we use these waves, we always use pulse. So the idea is that like one pulse sent and one can be received. So one pulse must return before the next one is sent. That is the idea. Otherwise, what happens? If we are sending a continuous wave, we cannot identify which one is a reflected one and which one we are sending. They will mix with each other. If we send a continuous wave, the wave strike and then wave bounce back. So we cannot identify So why we transmit the wave in a pulses, so that the one receive or one sent and one receive, like one pulse must return before the next one is sent. So one of the pulse must return when we send the second pulse, so that they don't mix with each other and we can easily identify. Otherwise, it won't be easy to identify that which one is the reflected pulse. In question 12, a source of sound moves away from observer at a steadily increasing speed compared with the original sound. The wavelength reaching the observer will be, so as you can see, a source of sound is moving away. So there is a source and the observer, and this source is moving away. So source is moving away, the wavelength which is received by the observer, that will increase and the frequency will decrease. And what about, because it is increasing the speed, so continuously the way, if the object is accelerating, so continuously the wavelength will start to increase, or it will become longer wavelength and continuously increasing. So when we check the options, the wavelength will not be shorter, so C and D cannot be an answer. We are left with A or B. So the wavelength, what the observer receive will be longer wavelength or a greater wavelength. And then because the object is increasing the speed, it is accelerating, so the wavelength will continue to increase. So longer wavelength or greater wavelength will be received, and this wavelength will continue to increase. So B will be the right answer. Is it clear, this question, that why the wavelength received by the observer will be longer, as well as it will continue to increase as the object is accelerating or speed of the object is increasing. Then question 13, when a fire engine moves away from the observer, so the engine is there that is moving away from the observer, pitch means the frequency. The frequency have decreased. This is because, what is the reason why the pitch has decreased? Pitch means the frequency, because as the engine is moving away from the observer, so the frequency will decrease and the wavelength which is received will be on the longer side. So the wavelength of a sound wave decreases. The wavelength is not decreasing, the wavelength is increasing. That's the speed of the fire engine increases. That is not the reason, because even if speed is increasing or decreasing, that does not have any effect on the frequency. The frequency of a siren, the source is there, so frequency of the source never changes. And then the distance traveled by each wavefront increases. As the wavelength increase, so we can also say the distance traveled by each wavefront will increase, or the wavelength has increased. So that's why D will be the right answer. In question 14, a sonic tape measure uses the ultrasound to measure the distance in buildings. It is sent out a pulse of ultrasound towards the distant wall and record the time interval between the pulse sent and its return. For one particular measurement, the time interval was 25 milliseconds. So, example, there's a wall and we send ultrasound. So that from the source it is sent and then bounce back. Calculate the distance from a sonic tape measure to the wall, sonic tape measure which is producing the ultrasound. As the speed of a sound is given 330, so whenever there is a reflection, the formula speed is equals to 2d divided by t. So speed is 330, 2 multiplied by d, and the time is 25 milliseconds, so 25 into 10 to the power minus 3. So this will be 330 times 25 into 10 to the power minus 3, which is 25 millisecond divided by 2. We'll get the distance. So the distance between the sonic tape and the wall is about 4.125 meter. Then the next part, the we use a pulse. Why is ultrasound transmitted in pulse? That's the same question. So reason the answer should be so that one pulse must return before the next one is sent, so that the time interval between the transmitted and the received pulse can be measured, or no overlapping of the pulse will occur, or no interference between the pulse or mixing of the pulse. Bats emit pulses of ultrasound to find the position of object using echolocation. The time between the bat emitting the pulse toward the building and the echo being detected is 0.045. Calculate the distance from a bat to the building. So example, there's a building, this is the same thing. So there's a building and the bat is emitting out this ultrasound. So this is 340 and this was 0.045, the time it took to bounce back. So when we simplify 340 times 0.045 divided by 2, so this will give us the distance between the bat and the building, which is about 7.65 meter. The next part, it's of 6 marks. So the bat is closer to its prey. The following changes take place. Like example, there is a bat and nearby there is a prey. So bat is closer to its prey. The ultrasound emitted by the bat become higher frequency. Like bat is sending the wave, what is sent by the bat and what the bat receives, that's having the higher frequency. That is one thing. And the pulse becomes shorter duration, like the time the pulse sent and received, that time becomes shorter. And the pulse are separated by shorter time interval, that's also the same thing. Explain why these changes are made, like why this happened. Number one, if the pulse which is sent and the pulse received its higher frequency, it means the bat and the prey, or prey and the bat, both are moving towards each other, or bat is moving towards the prey. So the first part, ultrasound emitted by the bat becomes higher frequency. So what is the reason why the bat is emitting out a higher frequency? When higher frequency is there, it will have a shorter wavelength. So higher frequency, because when we will give a short wavelength, and what is the advantage of using a short wavelength? So it will have less diffraction, because smaller wavelength will have, like the gap size depends on the, otherwise the diffraction can occur. So it will have a less diffraction. If it will have less diffraction, more of the wave will bounce back. That is one thing. That's why the bat is emitting out higher frequency. Then the pulse duration becomes short. So if we have a shorter pulse, means shorter wavelength, or shorter pulse, like the pulse which is emitted out, that is shorter, or the length of the pulse. And what is the advantage of using a shorter pulse? So we can get a more detailed image, so it can locate the prey precisely or accurately. So instead of sending the full pulse, like a longer pulse, the bats start to emit out shorter pulse. Like first say this was the pulse was emitted out from the bat, but as a result, when it is approaching a prey, it start to emit out shorter pulse. Shorter, like first it was example emitting out the duration for the pulse is say 0.7 second, but then the same pulse it is sending 0.35 second. So this 0.35 second, because it is shorter pulse, so when it bounce back, it can locate the precisely the position of the object as compared to a longer pulse, because shorter pulse increase the detail of the image. And pulse are separated. The pulse which are emitted out from the bat are separated by short time interval. So the pulse sent and the receive, like when bat is sending a pulse, receive, and then it is sending another pulse. Why not continuously sending? So that, so separated by short time interval. What is the advantage here? That so that the reflected pulse, so the reflected pulse does not interfere or combine or mix with transmitted pulse. So like sending one pulse, then receive, sending one pulse, then receive, then send another pulse, and then receive. So the advantage is like why pulses send, why pulses are sent. That is also a reason, so that the one which send and receive should not interfere. So when a bat is closer to its prey, the following changes take place. The ultrasound emitted out by the bat become higher frequency. Why higher frequency? So it will have a shorter wavelength, and shorter wavelength diffract less. Otherwise, what will happen? That the wave which is emitted out, so this is a prey. So when it is emitting out longer wavelengths, so what will happen? Instead of reflection, diffraction can occur. But when we use shorter wavelength, mostly the wave will bounce back, less diffraction. Then pulses become shorter, like the length of the pulse becomes shorter. First, like example, if it was emitting out a pulse for 1 second, then it's emitting out a pulse of 0.5 seconds, so that it can easily locate the exact position of the prey. And the pulses are separated by short time interval, like sending one pulse and receiving, then sending another pulse and receive, so that the pulse sent and the receive does not mix or interfere with each other. Is it clear? This question, that why the bats, when they are approaching a prey, increases the frequency of the wave which it is emitted out, the pulse duration become, or pulse becomes shorter, and this there's a time interval between the pulses of the wave sent and received.